So we are going to start the tutorial 3. So in this tutorial 3, we'll be discussing the deriving equilibrium constant for adiabatic and non-adiabatic chemical reactions. So in this particular tutorial class, I will first introduce you about the equilibrium constant, how it's actually important for deriving whether a particular equation is uh, proceeding towards the forward direction, whether it is achieving the equilibrium condition, okay, or not. Then we'll try to solve a problem related to that. So first comes the chemical equilibrium. Now, what is chemical equilibrium basically? As you can observe, I have given a small equation: 2H2 plus O2 is equal to 2H2O. So in this particular equation, 2 moles of hydrogen and 1 mole of oxygen is reacting and producing 2 moles of water. A very simple equation, we all know this equation. Now, this is basically only a general form of the equation, or a general form of chemical reaction. In practice, when you do a particular chemical reaction, it is not mandatory that all hydrogen what you supplied will react with oxygen and form H2O. Neither it is mandatory that all oxygen what you supply for a chemical reaction will participate and produce H2O. Okay, so this is one scenario. Another scenario is that the hydrogen and oxygen both are reacting with each other and producing H2O, that we all know. But is there a possibility that the reverse can also occur? Okay, whether an equation can go in the reverse direction or not. Okay, so understanding those scenarios at which the reactants react with each other and produce a product, okay, and how far it is producing the product, whether it is fully converting the reactants into the products, or the products again go back in the reverse direction and give you the reactants, or the how much quantity of the reactants what you have supplied in the chemical reaction are actually participating in the chemical reaction or not. The understanding of this is given by the chemical equilibrium. So how much a reaction is complete, or what is the criteria of chemical equilibrium, that means how far your reaction is complete or not, as we observe from a general chemical reaction of observation, is actually understood from the chemical equilibrium condition. Now, to understand the chemical equilibrium condition, we will describe this chemical equilibrium by two stages. Stage 1, or case 1, where we will consider the entropy principle of second law of thermodynamics. We know the entropy principle of second law of thermodynamics very well. Okay, so we will try to use this particular principle of second law of thermodynamics to explain chemical equilibrium. We know from the second law of thermodynamics that ds system is always greater than equal to del Q by T. So what is basically the del Q by T? So if you consider a system, say any system you consider, on the system you take a small section in the boundary, okay, and on this boundary the temperature is T, okay, and through this boundary there is an heat transfer occur, okay, a heat transfer occur, an elemental quantity of heat transfer is occur. It may occur in uh, the heat may go away from the system, or also the heat may come into the system. So both possibility are there. So if there is this amount of heat transfer is occurring through the boundary of a system whose temperature is T, then the del Q by T, the quantity, okay, what you can observe should be equal to ds system when you have reversible condition, okay, or reversible process. Okay, so if we consider the process to be reversible process, which does not have any internal irreversibility is not there, then the del Q by T will be equal to ds system. This we all know from the thermodynamics. Now, when this ds system can be greater than del Q by T, when internal irreversibility is there. For an example, frictional effect, okay, dissipative effect, those things already we have studied in thermodynamics, and we know that if because of these internal irreversibilities, is there if there is any change in the properties of the system, because of which some entropy generation ds gen is occurring, entropy generation is occurring, then this is the additional quantity along with del Q by T, which finally gives you the ds. So that's why ds, and in general we tell that is greater than del Q by T, and we all know that delta S gen is always greater than 0. This we all know from the second law of thermodynamics. Now, if the chemical reaction is adiabatic, okay, if the chemical reaction is adiabatic as well as the chemical reaction is reversible, and the chemical reaction is reversible, then okay, reversible, one is it is if it is adiabatic, del Q is equal to 0, okay, then there may be two cases, one is it is reversible, another it is irreversible, okay. So in this case we can tell that together with these two, irreversible and reversible together, we can tell that del Q equal equal to 0 for adiabatic condition, then ds system is greater than equal to 0. Okay, so this condition will be satisfied for adiabatic chemical reaction. So for we can write that for an adiabatic system, chemical reaction always proceeds towards increase in entropy. Okay, so when it will proceed towards increase in entropy, provided the system is reversible, irreversible. Okay, increase in entropy provided the system is irreversible. Irreversible if this is the condition, because most of the chemical reactions are irreversible in nature. So for irreversible for or for any actual chemical reaction, for an adiabatic system, the chemical reaction always proceeds towards increase in entropy. Okay, so when you are checking for a real chemical reaction, when you actually calculate the change of entropy for the chemical reaction, then you will understand that if the change of entropy for the system, okay, is uh, going to increase, okay, or increasing, then the chemical reaction is moving in the forward direction. Okay, if it is not happening, if the change of entropy is not happening for an actual chemical reaction which is in adiabatic in nature, then you tell that the chemical reaction may not be proceeding towards the forward direction. Okay, so this is very important, and that is how we can understand whether a chemical reaction is proceeding towards the chemical equilibrium or not. Now let us come to the case 2. Case 2, which where we have to we'll discuss that if a chemical reaction is non-adiabatic in nature, then what we do? If the chemical reaction is in non-adiabatic in nature, that means heat transfer is occurring through the boundary of the system, then we have to use the Gibbs function. Okay, so we have to use the Gibbs function. Using the Gibbs function, we understand whether a chemical reaction is proceeding towards equilibrium or not. Now we know that the Gibbs function is equal to G is equal to H minus Ts. Okay, where H is enthalpy, H is enthalpy. Okay, temperature, T is the temperature. Okay, and S is entropy. We know all. Okay, so the Gibbs function G is equal to H minus Ts. So if we differentiate the Gibbs function, okay, then we can write like this: dg is equal to dh minus tds minus s dt. Okay, so this is the differentiation of dg. Now we also know the equation of enthalpy. The equation of enthalpy tells you H is equal to U plus PV, where H is enthalpy, already we have told, and U is additionally here. Okay, U is additionally here. U is internal energy, and P is pressure, and V is volume. Okay, so pressure and volume and internal energy, the relation between them, that is U plus PV, we know this is enthalpy. Okay, so if it is the case, then again if we differentiate it, okay, the enthalpy dH, if we differentiate it, then we get dH is equal to du plus pdv plus vdp, basically differentiation of UV. Okay, now in this particular case, if we consider the chemical reaction to be occurring at constant pressure and constant temperature, okay, chemical reaction is occurring at constant pressure and constant temperature, then dt is equal to dp is equal to 0. Okay, for constant temperature and constant pressure cases, dt and dp is equal to 0. So the change of Gibbs function dg we can write as, okay, so dg we can write as du plus pdv. So this du is shifting over here. Okay, du plus pdv is shifting over here, and dt and dp becomes 0. Then we can write dg is equal to du plus pdv minus tds. Now we also know that, we also know from first law of thermodynamics that if del Q is the heat transfer through the boundary of the system, then neglecting all other internal energies except the intermolecular energy, U is internal energy in the form of intermolecular energy. Okay, intermolecular energy, and neglecting all other works except the boundary work. Okay, so the boundary work is PdV. Okay, so boundary work is PdV. Okay, if we consider the PdV work in the first law equation and considering only the intermolecular energy du, we can write del Q is equal to du plus PdV. So we can put the value of, okay, so first law of thermodynamics tells you like that. So from dg we can write du plus pdv, we can replace over there. Okay, so by putting this, we write dg is equal to del q minus tds. Now del q minus tds, as per using the entropy principle of second law of thermodynamics, we know that del q is equal to minus del q minus tds is greater than equal to 0. Or we have earlier also we have seen that ds is greater than equal to del q by t. So from there, if you take t this side, so t ds is greater than equal to del q, or del q minus t ds is basically less than equal to 0. So when we put this condition, then we get dg, change of Gibbs function, okay, dg is less than equal to 0. So it tells that for isothermal isobaric chemical reaction of fixed mass with PdV work, the reaction proceeds in the direction of decreasing Gibbs function. Okay, so dg either less than 0 or dg equal to 0. Okay, so when a chemical reaction is proceeding, okay, then if it maintains the isothermal and isobaric condition, that means if it maintains the constant temperature and constant pressure condition all the times during the chemical reaction, then the change of Gibbs function is either less than 0 or equal to 0. Okay, so less than 0 means initially say you started with a chemical reaction where initial Gibbs function is G1. Okay, then after certain amount of time, you find out the once the chemical reaction is going on, you calculate again the Gibbs function G2. Okay, by the way, how to calculate this, that also I will explain you. Then G2 is always less than G1. Okay, so when this is G2, that means proceeding Gibbs function of the mixture during the chemical reaction is less than the subsequent succeeding the values of Gibbs function. Okay, that means G2 minus G1 is always less than 0. Then chemical reaction is going on. Okay, and the chemical reaction will reach to equilibrium when finally you will see that this difference, this G2 minus G1 is gradually decreasing. G2 minus G1 initially it will be a big value, G2 minus G1 will be a significant negative value. Then this significant negative value tells you that the chemical reaction is proceeding towards the proper direction, towards the equilibrium, and gradually when the chemical reactions are going on, the difference between G2 minus G1 will reduce, and at a certain point of time you will find that G2 minus G1 is almost tends to 0. Okay, so G2 minus G1 almost tends to 0. At that time, tends to 0, at that time you tell that you almost reach to the equilibrium condition of chemical reaction. That means whatever the reactants you have supplied, all those reactants has been converted into the product. Okay, so that is basically how we can measure whether a chemical reaction is proceeding towards equilibrium or not. Initial cases we have considered, case 1 we have considered if the reaction is adiabatic, and in this particular case we have discussed if the chemical reaction is isothermal or isobaric, then how you will understand the chemical reaction is proceeding towards equilibrium. Okay, so equilibrium is achieved when the dg is for constant temperature, pressure, and fixed mass. That is also very important. When you are considering the mass is changing, then the equation will change. Okay, so you have to, for this condition to be satisfied, you have to maintain the temperature and pressure to be constant. The mass of the system has to be constant. That means the system has to be a closed system, and you cannot consider any other work except the boundary work. If these conditions are satisfied, then in this particular equation we can calculate the equilibrium condition. Now we again let us come back to Gibbs function and the enthalpy equation. So Gibbs function G is equal to H minus Ts and enthalpy H is equal to U plus PV. We all know this. Now if we differentiate them, okay, so Acha, G we can put the value in the equation of Gibbs function, we put the value of enthalpy. So Gibbs function becomes G becomes equal to U plus PV minus Ts. Now if we differentiate this uh, g, this Gibbs function, then we get du plus pdv plus vdp minus tds minus sdt. So what is this? This is a simple differentiation of Gibbs function. Okay, so if you do d of g, then d of u plus pv minus ts, what you are doing. So from here you can write du plus dpv minus d tds ts. Okay, so then from there if you do the differentiation, you get this equation. So in this equation you can just, if you rearrange the term, okay, then what you get, du minus tds, this tds you bring at front. Okay, so tds you bring at front. So if you take minus common along with pdv, then you get within bracket tds minus pdv. Okay, so tds minus pdv, we put it inside the bracket. Now tds equation, from tds equation, okay, we get another expression over here. Okay, so here basically we are obtaining this equation of dh. Okay, so tds is equal to dh minus vdp. Okay, ds minus pdv, I'm sorry, ds minus tds is equal to dh minus vdp. Yes, correct, vdp. So this equation we are putting in this particular place. In place of tds we are writing this. So we get dh minus vdp minus pdv plus vdp minus sdt. Now if you see this particular equation dh minus vdp minus pdv, then we can easily write d of h minus pv. Okay, because dh uh, minus vdp minus pdv, if you are writing this equation like this, then you can write dh minus, you take d common, then you can just make it pv. Okay, so d of pv is basically pdv and plus vdp, and since minus is there in beginning, so you can write like this. So if you can take common d from here, then you can write h minus pv. Okay, so in this way we write, and h minus pv is already there. Okay, so h minus pv, from this equation we can write h minus pv, this pv will come this side, then it is basically u. So in this particular equation we can write du minus du plus vdp minus sdt. Du cancels out, so you get vdp minus sdt. So bdp minus sdt is the final form of dg. Okay, without neglecting temperature and pressure changes. Okay, so for isothermal chemical reaction, if the chemical reaction is occurring in a constant temperature, okay, isothermal chemical reaction, then dt will be 0. Okay, and if we write the ideal gas law, if you introduce ideal gas law also, okay, so from ideal gas law, why we need to introduce, because here you have vdp. Okay, v is the volume, dp is the change of pressure. So from ideal gas law, pv is equal to nRut. So from here we can write v is equal to nRu nRut by p. Okay, why we write like this? Because we want to bring this p in this particular equation, so then we can do the integration. Okay, so isothermal chemical reaction dt is equal to 0, then we can write dg is equal to, we put the value of volume over here, nRut by p into dp. Okay, so now if we integrate from this equation, from the standard Gibbs function to a particular Gibbs function g between the pressure change, because you see temperature change you have considered to be 0. Okay, So that means isothermal condition. Then for the pressure change from P0 to P, if the Gibbs function changes from G0 to G, then what happens? So G0 is basically, this G0 is called as standard Gibbs function. Standard Gibbs function. Okay. Standard Gibbs function means what? That means if you want to have a standard state at normal atmospheric NTP condition, what is the Gibbs function for a particular substance? So from there, then the, because of the chemical reaction, the Gibbs function is changing, and at a certain point of time, when the pressure is P, at that time Gibbs function reaches to G. So if it is the case, then what is the equation? Okay, so the equation changes to like this. Okay, where G minus G0, that is basically the integration, G minus G0 is equal to N RUT. Now this is dP by P. So dP by P is ln P. So ln P with an integration range between P0 to P. So that is P by P0. Okay. So from here we can write Gibbs function for any species, that is GI. Gibbs function of any species, that is GI, is equal to GI0 plus NI RUT into ln Pi by P0. Okay. So what is this basically? What is I? I is basically the species for which you are writing the equation. I is basically say species 1, 2, 3, there may be 4, there may be n number of species may be present in a particular chemical reaction. So for individual species, you can write what is the Gibbs function for a particular amount of time. If the pressure is Pi, the number of moles of that species Ni, and the standard Gibbs function is NTP is GI naught, then what is the Gibbs function of that particular species? Okay. So for ith species, we can write like this. So we have understood how we can find out the Gibbs function for a particular species. Now using this Gibbs function, let us try to understand how we can explain the chemical reaction occurring. Okay. So in order to understand the chemical equilibrium, okay, we have to use an Van Hoff equilibrium box. Okay, so Van Hoff equilibrium box was the box which was given by a scientist named Van Hoff. Okay, and he told that let us consider that A moles of capital A and B moles of capital B are entering to a constant temperature bath. Okay, are entering to a constant temperature bath. Okay, after entering into the constant temperature bath, the partial pressure of A substance is Pa and the partial pressure of B substance is Pv. Okay, then in this constant temperature, why we have considered constant temperature? Because in earlier case, if you see in the earlier case, we have considered dt is equal to 0, dg is equal to pdv minus SDT. So there we have considered temperature to be constant. So to be synchronized with that, we have considered the constant temperature bath, which is also been explained by Van Hoff equilibrium box. After doing reaction between them, okay, they produce a product PC and PD for concentration where C moles of C and small d moles of capital D. So this is the chemical reaction which we are considering. Say A moles of small a and B moles of small b. So these are the reactants. Okay, they react with each other in a constant temperature. Pressure may vary. Then after the reaction, we get C moles of C and D moles of D, which are basically products. Okay, so if it is the case, then how the Gibbs function can be written? Okay, so this gives free energy for all the four species. Here, what are the species? The species are A, B, C, and D. Okay, so for all the species, how we can write the Gibbs free energy? Ga is equal to Ga naught plus A RUT ln Pa by P naught. This is for A species. For B species, Gb is equal to Gb naught plus B RUT ln Pb by P naught. For C species, Gc is equal to Gc naught plus C RUT ln Pc by P naught. And for the D species, GD is equal to GD naught plus DRUT ln PD by P naught. So these are the Gibbs function, or rather you can tell Gibbs free energy for all the four species A, B, C, and D. Okay. Now, if you want to see what is the Gibbs free energy change between the products and reactants, we have told earlier, no, that if your chemical reaction has to be proceeding towards equilibrium for a constant temperature and constant pressure system, your Gibbs function change should be less than equal to 0. Okay, so let us try to understand what is the difference of, how we can calculate the difference of Gibbs free energy between the products and reactants. So the total Gibbs free energy change delta GT is equal to G product minus G reactants. Okay, so what is G products? G products basically GC plus GD minus GA plus GB. GC and GD are the products, and GA and GB are the reactants. Okay, so for this, how we can write the Gibbs free energy equation? So for all the four species, initially we write the standard Gibbs functions changes for the products minus standard Gibbs function changes for the reactants plus RUT ln PC by P naught to the power C into ln PD by P naught to the power D minus RUT ln PA by P naught A into ln PB by P naught to the power B. Okay. I'm sorry. I think this should be, this ln will not be there because we are multiplying the products, and here also we are multiplying the reactants. Okay, so this will be basically ln of this. Let me write once again. This will be RUT ln. Okay, this will be PC by P naught to the power C into PD by P naught to the power D minus RUT ln PA by P naught A into PB by P naught B. Okay, so all P are small p over here. Okay, pressure we always write in small p. Okay, I hope it is understood. Now, from there, if we write in this particular form, GC naught plus GD naught minus GA naught plus GB naught is equal to delta GT naught. Okay, so delta GT naught is basically the change of change of total Gibbs functions, which are basically standard state Gibbs function. Okay, so delta GT naught is basically standard state Gibbs function change. Okay, standard state Gibbs function change. So this is GT, this is GT naught. Okay, GT naught. Okay, now we all know that if the chemical reaction should reach to the equilibrium, then delta GT should be equal to 0. Okay, total change of Gibbs function should be equal to 0. So using this delta GT is equal to 0, then this entire term delta GT naught plus RUT ln PC by P naught to the power C, PD by P naught to the power D divided by PA by P naught to the power A into PB by P naught to the power B. This should be this entire term should be equal to 0. So if this entire term should be equal to 0, then we can bring this delta gt in the left hand side of this equation, and we can write minus delta gt, okay, minus delta gt naught is equal to RUT ln PC by P naught to the power C into PD by P naught to the power D divided by PA by P naught to the power A into PB by P naught to the power B. Here, this particular entire term, this PC by P naught to the power C into PD by P naught to the power D divided by PA by P naught to the power A into PB by P naught to the power P, this entire ln of this entire term, this entire term, okay. So this ln will not be here, okay. So this entire term we consider to be the Kp. Okay, so when we put the value of Kp here, so we can write ln of Kp is equal to minus delta T naught minus delta Gt naught divided by RUT. Okay, so from this we can find out that here this particular Kp is called as the equilibrium constant. This Kp is called as the equilibrium constant. Now it is the ratio of the uh, you see partial pressure divided by standard pressure to the power C, okay, partial pressure divided by standard pressure to the power D, partial pressure of A divided by standard pressure of to the power A moles divided into partial pressure of B divided by standard pressure to the power the number of moles of B. Okay, so from there we can write Kp is equal to e to the power, because this ln will go this side and form e to the power minus delta gt naught divided by RUT. Okay, so Kp is equal to e to the power minus delta gt naught to the power RUT. Okay, so this is how the equilibrium constant is related to the Gibbs function, universal gas constant, and temperature. Now here, if we write like this, that the partial pressure Pi is equal to mole fraction Xi into the total pressure. We all know that the total pressure is basically the summation of all the partial pressure of all the constituents. Okay, so we can write Pc is equal to Xcp, Pd is equal to Xdp, Pa is equal to Xap, Pv is equal to Xbp. Okay, so from there we can write that what is Xc, Xd, Xa, Xb. Xc is equal to Pc by P. Okay, Xd is equal to Pd, Pd by P. Xa is equal to Pa by P, and Xb is equal to Pb by P. Okay, so these are the mole fractions. So these mole fractions, we can put this particular equilibrium constant equation, and equilibrium constant looks like this. Okay, equilibrium constant, this ln will not be here. Okay, ln will not be here. So Kp is equal to Xc to the power C into Xd to the power D divided by Xa to the power A into Xb to the power B into this pressure, this uh, total pressure will come. Okay, so total pressure divided by, because here you see you can replace it. Okay, Pc you can replace with Xc into P, Xd into P, Xa into P, and Xb into P. So from there, Xa, Xc, Xd, Xa, Xb, if you separate it out, then you can write P by P naught to the power C plus D minus A plus B. Okay, so this is an equilibrium constant equation. Okay, equilibrium constant. So what do you understand from this equation? You understand one thing very clearly, is that if Kp is more than 1, okay, if Kp is more than 1, then definitely the contents of the products should be more than the contents of the reactants, right? So in this way we explain the equilibrium constant. Okay, so equilibrium constant Kp is equal to e to the power delta gt naught divided by RUT, where Kp is equal to xc to the power c into xd to the power d divided by xc to the power a into xb to the power b into p by p naught to the power c plus d minus a plus b. So very importantly, two things we are clearly understand from here. So if delta gt is positive, okay, if the uh, delta gt naught is positive, then kp should be less than 1, then reactants are favored. Okay, so how? Because here you see, if delta gt is positive, then you have e to the power minus of something. Okay, so e to the power minus of something, if you are getting, then it should be less than 1. Okay, so then becomes kp less than 1. If kp less than 1, then that means what? Your constituents in the products, the mole fraction of reactants will be more than the mole fraction of the products. That means what? During the chemical reaction, actually the reverse reaction is occurring in a faster speed than that of the forward reaction. That means what? Your reactants are favored in this particular reaction, not the products. Okay, you will not be getting products, okay, towards the end of equation, because although the products were forming during the chemical reaction, but the reverse opposite direction, the reaction is speeding up and you are getting more and more reactants rather products while the chemical reaction is going on, and you will not get chemical equilibrium so soon. But if delta gt naught is negative, okay, delta gt naught is negative, that means standard Gibbs function change is negative, then you will see that negative into negative gives you positive. So e to the power positive, that means something always greater than 1. If something always greater than 1, then that kp is greater than 1. That means what? You see xc and xd, the mole fractions towards the product will be more than the mole fractions towards the reactants. What does it mean? It means that your chemical reaction is occurring in the forward direction. The amount of the product formation, the rate of product formation is higher than that of the rate of reverse direction or the reactant formation. As I told in the very beginning, that a chemical reaction can occur in both direction, in forward direction, in reverse direction also. But how will you understand whether the chemical reaction is moving in the forward direction or not? This is where you have to understand. Okay, mathematically, by using value, proper value, you will understand whether your chemical reaction is going to be completed, whether you will get a product favored chemical reaction rather than a reactant favored chemical reaction, and you achieve the equilibrium condition. Okay, so this is how we can actually calculate the equilibrium condition of a chemical reaction. So in this particular table, what we have shown here, you can see the standard state Gibbs function is given in the column number 4. Okay, if you see in the column number 4, the standard state Gibbs functions are given. Okay, this, the unit of this is kilojoule per kilomole. You can also write in joule per mole. Kilo can will cancel out. Okay, some of the values here will be requiring to solve one problem. Okay, so I hope this is understood how we can calculate the reaction rate constant, okay, or equilibrium constant, okay, with the help of the Gibbs free energy change. Okay, now with this, let us try to solve a small problem. Okay, so this is the problem over here. Here you can see the problem. It is told the decomposition of gaseous hydrogen peroxide occurs as follows. H2O2 gaseous is equal to H2O gaseous plus 0.5 O2 gaseous. What is the value of the equilibrium constant of this reaction at 298.15 Kelvin? Okay, so you see the temperature is fixed. Okay, temperature doesn't change. Here RU, that means the universal gas constant, is equal to 1.9872 calorie per gram mole Kelvin. Here the value of calorie per gram mole Kelvin, the universal gas constant is given. Okay, so we have to use the calorie value, not the joule. Okay, so let us try to solve this problem. First, if we know, if anybody knows what is the value of conversion ratio of joule and calorie. So the conversion ratio of joule and calorie, 1 joule is equal to, we know this is 0.239 calorie. Okay, so we need this to solve this problem first and foremost. Okay, so the chemical reaction is what? H2O2 gaseous is equal to H2O gaseous plus 0.5 O2 gaseous. Okay, so first let us try to find out what is the standard state change of the uh, Gibbs free energy. Okay, so Gibbs free energy, standard state Gibbs free energy for H2O2, H2O2, H2O2 is equal to minus 105,600 joule per kilomole. Okay, where you have sorry, joule per mole, joule per gram mole. Okay, joule per joule per gram mole. Let us write similar units, gram mole. Okay, so if it is joule per gram mole, then it should be minus 105,600 into joule to calorie conversion, right? So 1 joule is this much calorie, so into 0.239 calorie per gram mole. Okay, so this value comes around minus 25.238 kilocalorie. Okay, kilocalorie per gram mole. Okay, similarly, if you see what is the Gibbs free energy change for H2O. So Gibbs free energy change for H2O is uh, gaseous, right? So let us see from the table. Water vapor minus 241,820, right? So we write minus, I'm sorry, minus 241,820 joule per gram mole. Okay, so this will be minus 241,820 multiplied by 0.239. Okay, calorie per gram mole. Okay, so from here we will see that if we convert it, it will come around minus 57.790 kilocalorie per gram mole. Okay, and what is the standard state Gibbs function for oxygen gas? Here also it is told. Here you see for oxygen the standard state Gibbs function change is 0. Okay, standard state Gibbs function for oxygen is 0. So this is 0 kilocalorie per gram mole. Okay, so what is the change of change of standard state Gibbs function? Okay, total. So this should be is equal to the mole number of, you see, we have to write for product. First is the uh, product minus reactant. Okay. So what are the products? N moles of H2O into G naught. Now we can directly write G naught here. Why? Because the temperature here is mentioned to be 298.15 Kelvin. So G naught, okay, H2O plus number of moles of O2 into G naught O2, okay, minus number of moles of H2O2 into G naught H2O2. Okay, so how many moles of water is creating? 1 mole only. 1 mole into how much is the value? Gives free energy minus 57.79 plus this is entirely zero because G naught 0 is 0 minus this is again 1 into G naught H2O2. So H2O2 is minus 25.238. Okay. So after calculation, you will get minus 32.59 kilocalorie of the gives free energy change. Mole will cancel out, gram mole will cancel out because this is the mole we have considered 1 mole. Okay. So hence what is Kp? Kp is, you see the formula, we will use directly this particular formula. E is equal to minus delta G T naught divided by RUT. Okay. So Kp is equal to exp of minus delta G naught, GT naught, basically you can write GT naught divided by RUT. Okay. So exp of minus, okay, minus delta G naught. Now here we have to use calorie. So calorie means 32.59 into 10 to the power 3. Okay, divided by RU. Why we have considered calorie? We have not considered calorie because RU is given in calorie. So 1.9872 into what is the temperature? 298.15. Okay, 298.15. Okay. So from here, from this particular value, acha, one thing I have not written here, you see this is minus of delta G. Okay, so this is minus of this minus, so minus minus will become plus. Okay, so minus minus will become plus exponential of something. Okay, so if it is plus then exponential of something, definitely it will be a what? It will be, let you do the calculation at your home. This calculation let be a homework, but definitely you understand this should be greater than 1. Okay, Kp will be greater than 1. If Kp is greater than 1, then the reaction is what? Product favored. Okay, so this is how we can solve a particular problem and we can understand whether the reaction is product favor or a reaction favored. Okay, these are some of the homework problem I have attached here. Try to solve this homework problem. Okay, so that it will be helpful for you. Okay, is there any query? Anyone? Any doubt? from the participants.